Hello children, welcome to channel Sube. Children, today I am going to discuss question number 7 from the MCQ part of 2021 Physics New Syllabus paper. The breaking strain of an aluminium rod is 0.2%. What is the minimum cross-sectional area of the rod to withstand a force of 3.5 times 10 to the power 3 Newton? In brackets, Young's modulus of aluminium is 7.0 times 10 power 10 Newton per square meter. There are answers in square meter. There are 5 answers. So children, without going directly to solve the question, I would like to revise the lesson a little bit, otherwise because you will not understand, the equation is a little bit complicated. So therefore let us discuss the lesson a little bit. So let's say if we have a string or a wire like this, steel wire say, there are steel wires in the laboratory, you must have seen. So this one is the ceiling or a support, fixed support, not moving, strong support such as a ceiling. So we fixed the wire that we have about length maybe about 2 meter, that is enough. So we know that it is a solid because it is a steel. What's going to happen if we apply a downward force on a solid? What do you think is going to happen? Let's say if we hang a mass on it like this. If you hang a mass on this on it like this, that means a weight. There are weights in the laboratory. So if you hang a weight like this, so now we have given a downward force to the wire. So all solids have the ability to stretch beyond their natural length. So this length is the initial length or natural length. So say simple L, the natural length is simple L, we can measure it using the meter rule in the laboratory. And now we have applied a weight on the wire, so the wire is stretched, you can see now, and the amount in which they stretch depends on, let us draw the levels like this, from this level to this level. Now the wire has been stretched. The amount in which they stretch depends on the force, and that's applied. So here we have a mass hanging on it, and the downward force is equal to the weight force of that mass. So we can write the force is equal to mg. So downward force is equal to weight force. So what happens? The wire is now stretched. There is a difference in lengths now. So this length is called extension. This length is called extension. So this extension is very small. If you increase the applied force, the change in length, this length and this length, the change in the in length will increase. This one will increase. Now let's make a graph that describes the force and the change in length. Change in length means this extension. So now we are going to do a little experiment. We measure this value f. How we can get the reading from the tray, this weight tray is there. So the mass of the weight we have fixed there, so we can get the force, and we can measure this extension using a special caliper is there. The scale, there is a special scale like this. It contains a vernier scale and a main scale like this. You might know. If you have done the experiment, you know it. So there is a special sort of scale. So using that scale you can, however, find out this E extension. So now we can fill a data sheet like this. You can fill a data sheet like this. F, the force to one column, and the extension to the other column. So you take the readings by adding weight by weight. Sometimes 0.5 kilogram, that means 500 grams by 500 grams, or 200 grams by 200 grams, little by little you add weights and take this extension, and again you remove that weight and take that extension again. Then only you can ensure that the wire is the length of the wire is increasing while the weight is being added, and also the length of the wire is decreasing while the weight is being removed. So that way you can do the experiment and fill this, take down the readings like this, and you can plot a graph taking force to the y-axis and taking the extension to the x-axis. Initially we get a graph like this. Initially there's going to be a linear relationship between F and E. So like this. Then after that the relationship won't be so linear. It will be like this. You get a little curve shape like this, and then after what happened? It will be like this, like this. That is what you will see. And then after that the relationship won't be so linear from this point. So it's going to be curved like this. Let's call this points. Let's name this point. Say this one is A. At the end of this linear part, B, and this place C, and it will go further like this, further like this, yes, like this, and a little bit we can draw, or maybe like this, the shape. So the point, say this one, D, this point is D. So now this point B is called, proportional limit. This limit is called, this point is called proportional limit. Then this point C, this point is called elastic limit. So this point D is called breaking point. So all this is wording. Point C is the elastic limit, point B is the proportional limit. So in the region between this A and B, where it goes up to the proportional limit, that region, notice that it is linear. This region is linear. That's why we say to this limit the proportional portion. So at the end of that portion is called proportional limit. So from that beyond that limit it is called the elastic portion. So that the end of that portion is called elastic limit. So here's where the wire actually the string break into two pieces because the load is too much. So children, since this region is proportional, that means F is proportional to E, so we can write F is directly proportional to E extension, because that region has a linear shape. That region has a linear shape. Therefore, it is the mathematical relationship for such a shape, is this one. Proportional, we say proportional, directly proportional. F is directly proportional to E. So we can write that F equals Ke. So this is what we call Hooke's law. This is what we call Hooke's law. So children, what is Hooke's law in words? If the proportional limit is not exceeded, so you must say this word, this term. If the proportional limit is not exceeded, the extension is proportional to the load. Load is F. Load means this F, force. So that valid, that rule, that law is only valid up to this point. Beyond this point, it is not valid. For this region, you can apply it. It is valid for this proportional limit. That is why Hooke said, if the proportional limit is not exceeded, that means you are in only this region. You can't go beyond that. That is the Hooke's law. So now between this A and C up to this limit, we have something that's known as the elastic region. So this region is called elastic region, because the property, it is a property, the elastic property. Elastic property is still remaining up to this place, but the proportional property ends at this point, and beyond that you can't see the proportional property, but still the elastic property is there. Elastic property is there, but in this region it is not proportional, but however the elastic property is there still up to this point, this limit. That's why it has been named, this region is named as elastic limit. So if I explain a little bit more, now the elastic region is basically, this region is basically the region where it is elastic. The material is elastic. That means if you remove the external force, that there is a force here like this, every point has a force. So if you remove that force, that means if you remove the external force, the object will return to its natural length. Object will return to its natural length. That means to this length, to this level. It returns to this original level, or we can say to the natural length. Then it will be deformed, return to its natural length. It won't be deformed. It's going to regain its original shape. It is not going to deform. So this region, it is it gets deformed. So in this region, the material doesn't get deformed. So therefore the bonds are not broken in the lattice. So it has the ability to return to its original shape. In this region I am talking, from here to this point, point C. Now after this point, this region, so you are leaving now the elastic limit. Once you pass point C, that is the elastic limit, this one. So you enter a different region. This one is a different region, something known as plastic region. This region is known as plastic region. So let us write it here. So in this region, if you stretch it too far, then it will lose its the elasticity, the property, the elasticity. It won't be able to snap back to its original shape. And so by applying a force that's too high, like this, too high or too much, then you could permanently deform the solid in this region. If it doesn't return to its original shape, that means actually if you remove the force from here, it follows this line. It follows this line down. If you remove the force from here, it doesn't follow this line. When you increase the force, it followed this line, but after this elastic limit, actually after this elastic limit, so we can say this place somewhere like this. After that elastic limit, if you remove the force little by little, it doesn't follow this path. It will follow this new path. You can see it if you do the practical. So we couldn't label this region as elastic region. We only discussed this region is called elastic region up to this point. After that, this region is called plastic region, because plastic deformation is occur at that region. That means the bonds between the molecules break little by little, not all together. Little by little the bonds break and the shape of the material permanently change. That means deforms. The plastic deformation, we say, the process is called plastic deformation. This region is called plastic region. So the word plastic is that. So children, now I described the shape and the words that we use in this lesson. So if somebody asked in the exam, say explain, in the essay part, explain what is meant by elastic property. So how do you answer it? So the question is, explain what elastic property is. So try to answer this. Explain what elastic property is. So you can say, under an applied external force, if an object changes its shape like this and returns to, you must write that part also, returns to its original shape after removing the external force, then it is called elastic property. So like that you can collect words to write a suitable answer like this. Under an applied external force, if an object changes its shape, means length, width, height and everything, and returns to its original shape after removing the external force that is given, is called the elastic property. So like this you can write. This part also essential, because you won't get only if you explained the increase or decrease the length after applying an external force. That is not enough. You must write returns to its original shape. This part also you have to write after removing the external force is called. Because in this region also, when you apply a force, the length of the wire increases, but it doesn't decrease after removing the force. So therefore this part is not called elastic, it is plastic. You know normally now what you know as plastic, it's like that. So this explanation is like that now. Children, now you know how to explain if in the exam, if they ask explain what elastic property is. Under an applied external force, if an object changes its shape and returns to its original shape after removing the external force, is called the elastic property. So keep that in your mind, because from time to time they ask in essay papers that. Because most of the children write when applying a force, the length of the wire increases. That's all they write. So you don't get marks for that. Because in this region also that happens. When you apply a force, when you increase the force, the length increases. But it doesn't decrease when you remove the force. That is the difference in this region. So therefore you have to point out that you are talking about this region. Then you have to write, you must write when removing the force, the length decreases. That part also. So let us focus our mind to this breaking point. Now if you apply from here, we are going upwards. If you apply too much force means now you have passed this elastic limit even. We were discussing this elastic limit. Now you are applying more force to the wire, too much force to the wire, little by little. If you apply too much force, then you could reach this like that breaking point, at which point the solid could snap, the wire could snap into two pieces. It can fracture, break, and so that's the breaking point of the material. That's the breaking point of the material. Now the ultimate strength has obtained, the wire has obtained the ultimate strength. The wire can't go beyond that. And also the maximum force just before the breaking point, maximum force the wire has obtained. We have given the maximum force. That is the maximum force that we can give to that sort of wire, to that particular wire. That is the maximum force. But in practical we don't give that force because that is very dangerous. We don't use these regions. We stay only in these regions. Even less than that, we only stay in this region. We don't go there when they make bridges and all that. So that is the maximum force theoretically, but practically we don't reach that. This is the maximum extension at that for that wire. This is the maximum extension. So keeping that in your mind, so we are going to plot another graph. So here we took F for the y-axis, E for the E means extension, for the x-axis, force directly, the force to the y-axis. But we can plot another graph from which we can obtain more useful results. Let us see now it. So children, we can plot another graph without taking just F to the y-axis and E to the x-axis. Instead, we divide F by A. A means area, cross-sectional area, and we take that term, that variable, to the y-axis, and we divide E by L. L means the initial length, original length of the wire, natural length. So we divide extension, each extension. So we got lot of extensions here. We divide each extensions like this, having a column like this. E divided by L. So we can L is common. Here you can write initial L is this time, this much, say 2 meter, like this, and we divide each extensions by that constant initial length. So we get values, and we can plot the graph like that. So this special term is called stress. It is called stress. Alone this F is called force. You know that F divided by A is called stress. So this alone E is called what? Extension. But this term, the whole thing E divided by L is called strain. So this wording should you have to keep in your mind. This lesson is a little bit difficult. That is why there are a lot of words that are not familiar to us. So therefore you have to use these words, write or speak with others or teach to somebody, then you can get them familiar, then it will be easy. The problem is this wording. So F divided by A is called stress, then E divided by L is called strain. So along this E is what? Extension. So like that. This one is initial length. So this one is area, cross-sectional area. This one is force. So like that, if we plot the graph, we get the same shape. Nothing is changed. Everything exactly matched to the previous one. Because why that happened? Because this A is a constant. We divided F by a constant, so nothing happens. So we divided this E by this L is a constant. So we divided this E by a constant. So the relationship doesn't change. So therefore we can write. So regarding this part, that means the proportional region, proportional up to proportional limit, proportional region. For this region we can write, because it is a straight line, isn't it? Since it is a straight line, we can write this strain is proportional, directly proportional to stress. So F divided by A, like this we can write. E divided by L is proportional to directly F divided by A. That means the stress, the strain is proportional to, this one is strain, is proportional to stress, directly proportional to stress. But you must mention not everywhere, where? Only in this region. How to say that? If proportional limit is not exceeded. If proportional limit is not exceeded, that means anywhere you can stay here, but not beyond that. So when you write this relationship, you must say that. So let us do it later. Let us discuss this relationship first. So stress is this one, strain is this one, E divided by L. So we can write then stress equals K times strain. So K equals what? Stress divided by strain. So this one is a constant. That is the gradient of this graph. That is the gradient, because this height is F by A, this length is E by L. So what we have now received, stress is F divided by A and the strain is E divided by L. So the gradient of the graph, so gradient is constant. You can see everywhere up to this limit, gradient is constant. So that is an important output we get from the graph. After plotting the graph, we can find out the gradient. So that is a constant. Depends on the material, not the object, not the wire. depends on the material. So therefore that constant is specially named as Young's modulus. Young's modulus. That one is called Young's modulus. So we write therefore the letter Y for this K. Instead of K we write the letter Y because Young's modulus. So some people write E. In some textbooks you can see E because some people say elastic modulus, therefore they use capital E, but we use Young's modulus, the Y symbol for that. So Y equals then F divided by, using symbols F divided by A, then whole thing divided by E over L. This is the final equation. This is how we get it. So this equation you can use if the proportional limit is not exceeded. In this region, if you are sure you are in this region, if a problem is given to you and you can identify that what they talk about is inside that region, so then you can apply this equation. So children, now we are going to little by little approach our problem. So here this is strain, this is strain. So I used this word to name this term. So this is special point, look at this special point. Let us use purple color. This is special point just before the breaking point. What is this? This is an E extension. This is an extension because there are a lot of extensions here in this data sheet. Also there are a lot of extensions. So there is the maximum here, the maximum, say this one is the maximum. So the maximum just before wire breaks. So this value, what is it? How can we denote it? This value E max or E breaking points, just before breaking point we can write it E breaking or B-R-E-A-K-I-N-G, breaking, E breaking. We can write E breaking this value, and L is constant however. So we can write the strain here, the strain is strain, not T. This value is directly divided by L, not only E divided by E breaking divided by L. L is a constant. E is the special value, the specific value just before breaking point. So E breaking, that is special value, divided by the original length, we can call it breaking strain breaking, because at that time wire breaks. Strain, T-R-A-I-N, strain but breaking. So this value then refers to this value, stress breaking. Stress in brackets breaking. Stress breaking. So they have given in this question one of those values, strain, breaking strain of aluminium is 0.2%. So that means here this value is E breaking divided by L is equal to 0.2%. What is percent? What is the meaning of percent? per 100. The denominator should be 100, then 0.2. This one is the meaning of this symbol. You know that. I don't know whether you know or not. They have this problem. They have written this problem like this because the people who don't know this mark, this symbol, to convert it to this ratio, are in trouble. They can't solve this problem. So you should be able to convert these types of things into, sometimes they say average or like this, sometimes they say ratio, sometimes they say percent, like this. So you have to change it into this ratio. So you have to just take in that equation simple L as 100, simple E as 0.2. That is what you have to do. So they have given E divided by L equals 0.2 divided by 100. That is all. So let us use this equation now. Young's modulus, they have given 7 times 10 power 10 as I remember. Let us see. Yes, 7, 10 power 10, 3.5, 10, 3, 3.5, 10 power 3, the force, 3.5, 10 power 3, the force is. The area we don't know. Let us write area. We can take this area to the down to the denominator. So let us write it here. Then E divided by L here, this one. I write it as it is without changing. E divided by E is 0.2 now, divide by 100. Percent you take as 100%. 0.2%. Percent you take as 100. So this 100 goes up. So now we can take it to the numerator. Therefore this one goes to the numerator like this. So we delete this one. So this is solved now. You have to simplify. So 2 zeros, 3, altogether 5. Then here 5 remaining. Then A we take to left. Then 3.5, everything cancelled. Then 0.2 is remaining here. Then this 7 goes down to this place, to the denominator. That is all. Then 10 power 5, we just jump to this say, then it becomes 10 power minus 5. We don't take it down, just you can jump over the equal sign. Then you have to change the index, the sign of that index. So minus 5, 10 minus 5. So now 3.5 times how many? To 7, 2. Then 10 power minus 5 divided by 2 times 0.2 is 0.4. So we can write it 4 10 power minus 1. Then 1 over 4 times, then cancel this one, then minus 4 here, 10 power minus 4. Then what is 1 over 4? 0.25. You don't have to divide, you must remember these things. 1 over 4 is 0.25. Then power minus 4. Then from here 4 times go left, but if you write 2.5, then 10 minus 5. What is the unit? What did you find? Area, cross-sectional area of the wire. So it is going to be meter square meter. 2.5, 10 power minus 5. 2.5, 10 power minus 5. So this one is the answer. This fourth one. So you don't have to do all these things. I explain these things because if you don't have a background, you don't remember the lesson, or you are not learnt this, or you missed this somehow from the class or from the school. If I write directly this equation, you will be in trouble that so I thought. So that is why I revised you the lesson. So this equation, using this equation, if you remember this equation properly, you just have to start from here. From here you have to start, use this equation. Only this part you have to do in the real-time examination if you remember the lesson. But those who remember the lesson, no need my help, because this one is a very easy thing. If they identified that this one can be written like this, very simple. But for those who don't know this equation and who hasn't learned this lesson, and who has left this lesson, some people leave these lessons thinking that they are difficult. So I think now you can cover it. This is not difficult. If you remember these graphs, how behave these wires when we apply forces, and what are the limits where we can apply these rules. So then if you remember those things, you can pass the exam easily. So keep these things in your mind, but just you can't keep, actually you have to use these things as we do, as teachers do, because we teach daily, so we remember. Therefore we don't have to we don't forget, because we use it. If you don't use it, normally you forget, that is normal. So therefore you have to daily you find somebody to teach, and some junior person, junior one, and you can teach daily. Then that will benefit beneficially, that will benefit both of you. Therefore so I think you understood. I don't know, this lesson is not difficult, So I discussed what this Hooke's law and this Young's modulus, and also I have to discuss, I think better discuss this energy also. So let us now go to that one. So now we have finished, we have done this lesson. This problem is okay, we have finished, we have done this. We have choose the answer, so it is the fourth one. So let us go to the next thing what we are going to discuss. So now children, to complete this section, let us discuss the energy, elastic energy or strain energy, and the both words are used. However, energy is stored in a stretched wire. So this, if the wire is stretched, the energy we can calculate how it is. It must be equal to the work done. So how to find out the work? Work is force time the distance or the displacement. So the wire, we use this like this. So initially it was like this. After stretching, it's like this. The extension is this one. Extension. The force at the beginning is 0. Force at the beginning is 0. Then force at the end after stretching the wire, that is what we take down as a reading. F equals F. When we do this experiment, at the beginning we don't, when the weight is on our hands, before we release it, we don't take the readings. After releasing the weight that is attached to this wire, after coming to the equilibrium position, that means no motion, so after a certain time we take down the readings. So therefore the final force is F. It is equal to F that we take down as, it is mg or whatever it is, that is referred to the final force. So here the force must be constant. If you use this equation along all the way this distance d, the force must be constant. But from this place to this place, this point to this point, along the way along this distance e, the f is not constant because initially it was 0, final value is f. So it increased little by little in this small time period from 0 to final value f. Therefore we have to use a mean value for this f instead of a constant value. Therefore we have to convert this to a constant value, that is the mean value. So how to take mean value? The first value plus the final value, 2 items, therefore divide by 2. So distance is what? What is the distance? So let us arrange a little bit here. Distance is e extension, so we get here extension. So f divided by 2 times e. So therefore we write, so this is the work done or energy. We can write energy equals half Fe. Energy equals half Fe. So this is the equation we used to find strain energy or elastic energy. That is a sort of potential energy. In that category, potential energy, it is a sort of potential energy. So children, now we can go further. There is another equation to find out the energy. We can use this Hooke's law. This equation we can use to go further. Let us take it here, that we discussed previously. So now we can substitute from this Hooke's law. Energy equals half times, instead of F we can write K times E, and this E now E. K times E means this one in blue, like this. Right, now clear, isn't it? So what we get? E equals half times K E squared. This is the second equation that we can use to calculate energy, potential energy or strain energy or elastic energy. All are same. So sometimes we write E equals half kx squared. Instead of E, some people write x, because in mathematics they use x instead of E. So this equation also the same. Half kx squared, half kx squared. So that is easy to say than half ke squared. So that is difficult. Therefore, most of the people use this equation, but however it doesn't matter. Whatever the equation you use, you get marks. If you use it correctly, you get marks. So this is the equation to get the total energy in the wire. Total energy stored in the wire. So then there's another equation to find out the energy density. So that is called energy density or energy in unit volume. So the wire, assume like this, we used a wire like this. So this cross-sectional area is A, this length is L. So the total energy we know now, this amount, total energy is this amount. Then how to find out the energy in 1 cubic meter? 1 cubic meter, say this volume is 1 cubic meter. Volume equals 1 cubic meter volume. Then this one is the total energy. If we divide this by the total volume of the wire, then we get the energy in unit volume. So the volume of the wire equals the equation we have to use, what we use to find out the volume of a cylinder, cross-sectional area times length. So A times L is the volume. So this E energy, if we divide by that volume, what we get, what we need, this one, energy per unit volume. So this equation, now we have to divide kx squared by A L. X means E, no, we use that other equation, not this one. We have to use this one, not this one. There are two equations. Let us use this one, the same, this one and this one same. Equation 1 and equation 2, half Fe. Here we have to use half Fe equation. We can derive from that equation also, but we have to go along a long path. So therefore, let us use this equation. So energy is half Fe. So we have to divide it by A L. So this part is what? That is stress. F divided by A is stress. Then what is this part? Strain. Then times strain. What we get, there is a half also. This is the energy in an, or we say in a 1 cubic meter volume, or we can say unit volume. So this is the equation. Or we can write energy for 1 cubic meter equals half F divided by A times E divided by L. So using this equation, you can find the energy stored in a unit volume of the wire. So that part is done now. So children, let us do something else. Let us go to Hooke's law. We learnt it here today somewhere. Here it is, Hooke's law. So here, what is this K? It is the proportionality constant. So you can subtract, you can find it, you can find a term for that using, let us do, you can write from here K equals, we are going to find out what is the meaning of this proportionality constant, F divided by E. We isolated K, F divided by E. But we know Young's modulus equals F divided by A, then E divided by L, means we can write above the line like that. So this one is K, this one is this K. So let us write Y equals K L divided by A, K L divided by A. So K equals Y A divided by L. This is K, Y A divided by L. So the original Hooke's law equation is F equals K. So we can write F equals, K means this term, E, like this. So that also a useful equation. So keep that in your mind. The K is this term coming from Hooke's law. And finally we can go to dimensions. Dimensions of Young's modulus equals dimensions of F. Let us write first F divided by A like this, inverting this E and L, we take A down, then dimensions of F, so dimension of total thing, dimensions of Y, Young's modulus equals dimensions of F. F is ml T minus 2, mlt minus 2. So divide by this one, L squared. Dimensions of A is length times breadth, so therefore both are lengths, so L squared. So these people has no dimensions, they have no dimensions, because no dimensions, equal dimensions. So this one has dimension L, this one also has dimension L, because this one is the original length, so it is a sort of length. This one is the extension, the difference between lengths, or the stretched length, so that also a sort of length, so they cancel each other. So finally M L minus 1 T minus 2 is the dimension of Young's modulus. So since this strain has no dimensions, only the dimensions of stress is stress divided by strain, that way also you can take Young's modulus. So this one has no dimension, strain has no dimension, no dimension. Then dimensions of Young's modulus equals dimensions of stress. Next time you might get this question. This time they had asked work and energy, dimensions of work and energy, so they are equals. So this also equals, equal dimensions these people has. So I think I discussed everything, complete everything I discussed. So children, I think you might be happy, because if you missed the lesson in the classroom or in the tuition, now you can cover this. Now you can take down this note even. So I think you are happy. I don't know. If you are happy, please subscribe my channel before you leave. So see you tomorrow. Goodbye.